Hey everybody, now that we've introduced inductors and capacitors, let's start combining them with resistors. So if you look here, we have some, what we can consider a Norton equivalent of a more complicated circuit. If we do a source transformation, we could turn that into a Thevenin equivalent. So the source here could be represented by just some equivalent circuit. And what we have here is a switch. Let's talk about that. So when t is less than 0, the switch is closed, completing the circuit. And then at t equal to 0, the switch is going to be open, breaking the circuit, and so all of this is out of there. Now when the switch is closed, what's happening? This current source is feeding current here and here and here. And if we wait a long time, I will explain this in a separate video. If we wait a long enough time, everything is going to be constant. The voltage everywhere is constant. The current everywhere is constant. Now, that's something interesting. If the current through an inductor is constant, what does that mean? What's the voltage across an inductor? L di dt. So if the current is constant, look at this. The time derivative of a constant is 0, which means the voltage across the inductor is 0. Voltage across the inductor is 0 means it's like a wire. It behaves as a short circuit. Right, so imagine this is just a wire. That means the current here, feeding here and here and here, there's no way this resistor will get any of the current. Neither will this one. Neither of those resistors get any current. The inductor hogs all of it. So the inductor takes all of the current when the switch is closed. So all of this. These get nothing. Okay, now when it's time to open the circuit, all of this is gone. This is out of there. So all we have left is an inductor with some current that we know, right? It's this. And then it's connected to this resistor. And immediately before we open the switch, the current was this. What about immediately after? Could it change instantaneously? No ways. It's impossible. Recall, like say if you have a current going through the inductor that looks something like that, then what's the voltage? L di dt. So it's proportional to the time derivative. So it's the time derivative of a constant, 0. What's the time derivative of this? Whatever the slope is. And here, constant, 0. So if you look at it, the voltage across an inductor can change instantaneously, but there's no way the current can change instantaneously. The only way for the current to change instantaneously is if the voltage is infinity. So it's impossible. So that means the current, when the time is 0 approaching from the left side, like the limit as it approaches from the left, has got to be the same as the current at 0 when the limit approaches from the right. So if it was this before we open the switch, it's got to be this immediately after we open the switch. But then what happens after that when t is greater than 0? How do we do that? So let's follow this current around this loop and write KVL. So KVL, what's the voltage here? L di dt. And then this current is the same over here, right? So what's the voltage this way? If the current is going this way, then it's going to be positive IR. And then that's it. So this is KVL. So we need to solve this for I. Now, how do we do that? This is what's called an ordinary differential equation. And this particular one is first order. Ordinary differential equation. Which you wouldn't really say that. You would say ODE. Ordinary differential equation. ODE. Differential equation because there's a variable and its derivative. So for example, if we had another one over here, right? So it's like variable, first derivative, second derivative. That makes it a differential equation. Ordinary because it's just the derivative as opposed to like a partial derivative like this. That would be a PDE, partial differential equation. So we won't deal with that this semester. First order because the highest order is 1, as opposed to if we had something like over here. That would be a second order, ODE. We'll deal with that in a few weeks. And if you want to be super nitpicky about it, you see how this is a 0. So this is a homogeneous first order ODE because this is 0. If it were non-zero, like if it was 100 or something, then that would be a non-homogeneous first order ODE. We'll do that pretty soon, like in a couple of videos. And if you want to sprinkle a little bit more detail, see how these coefficients are constant. So this is a homogeneous first order ODE with constant coefficients. Okay, and what's important now is how do you solve it? So we're going to use a technique called separation of variables. And the technique is, you see how there's I over here, T over here. We want to get one variable, the current, on one side of the equation, the other variable, time, on the other side of the equation. So let's do that first. So how about I move this on the other side? Okay, and then let's move L over here. All right, now let's trade this and this. Okay, so let's trade places. So then we have di over I, and then minus r over L dt. So there we go. We successfully separated variables. I on this side, t on this side. Now we just go like that, integrate from t equal to 0 to some other time later. I at t equal to 0, I at t. I'm just going to call this I naught, just so less writing. Okay, and let's integrate this. So what is integral di over I? Natural log, ln. Okay, and then here, minus r over L, t minus 0. All right, and we can always rewrite this like that, same thing, right? Now, how do we deal with this natural log? What's the inverse? Exponential function. So check out this trick. Okay, remember that trick forever. You can always rewind the video and see that again. These are inverses. So then we just have I of t over I naught equals e to the minus r over L t. And let's just move this right over here. Okay, here we go. That's the current, and that's the technique to solve a first order ODE. Okay, one more little detail. You see whatever is sitting right here, whatever value is right there, if you take the reciprocal, we call that the time constant. So I'll replace that with the reciprocal of tau. For tau, so in this example, that would be L over R. This is called the time constant. And it deserves its own video. So I'll stay tuned for that one. about the time constant, and it's going to tie directly to this whole waiting for a long time thing. Those go together. So I have a separate video for that. Okay, and for the resistor here, if we now know the current, what's the voltage? Ohm's law, right? Just use Ohm's law. So the voltage, let me just write it on the side over here. Just IR. So just that times R. Okay, so there's the voltage across the resistor. What about the power? The power would just be VI. So this times this. So let me just multiply those two things together. So we got I naught R, I naught. So that's I naught squared R, e to the minus R over, this should be a, sorry, this should be an L. I wrote it messy. That times that. So there's two of them. So two of them, e to the minus 2 R over L t. Okay, so that's power. What if you want energy? If you want energy, so that would be the energy absorbed by the resistor. Then you just integrate this over time like that, right? From say 0 to t. So if you integrate that over time, you get I squared R. And then if you integrate that, that would be, let's see, the reciprocal L over 2R e to the minus 2R over LT from 0 to t. Okay, and then let's finish evaluating that. So from 0 to t, that would be like this. And let's clean up that mess. So, okay, that's so that's 1/2 I naught squared. Let's see, L I naught squared R over R, and then see that minus sign. Let me just multiply it through here. So that leaves us with 1 minus. Okay, so this is the energy absorbed by the resistor. All right, so I wanted to keep this video short because this is a lot of information to absorb. So I'll see you in the next one where we talk about the time constant. Okay, I'll see you in that video.